The poet Edna St. Vincent Millay says, Euclid alone has looked on beauty bare. And the German philosopher Kant says that the universe is structured by Euclid's principles. So Euclid's Elements, written by Euclid, has been called the most influential textbook of all time. It's been called the birthplace of deductive mathematics. It's been called the origin of the mathematics we call geometry. And almost all of those claims are false. But one thing that really is true is that Euclid's Elements introduces a style of mathematical writing that is with us today. And it's famously said that there are sort of three signatures of mathematical writing. Three ways you know that what you're reading is a math text instead of anything else. The first is it's decontextualized. So geometry, the word means measure of the earth. But here's a whole book about geometry that doesn't mention the earth once in it. So it's separated from the worldly context. Second, mathematics is depersonalized. There are no characters in this story of the Elements. There are no heroes, there are no villains. There's one pronoun, I, that shows up a number of times, but the only thing I ever does in the Elements is to say, I say the base angles are equal, or something like that. You never learn about who this I is. And the third, and an interesting one, and one that really does start exactly with this text, is that mathematics is detemporalized. It makes no mention of time or of motion, which is change of position in time, and no arguments can be based on this. And in fact, if Euclid were here, he would be very nervous about the title of my talk, A Dynamic Geometry Perspective, because one of the things Euclid sets out to do in the Elements is essentially to remove time from mathematics, to kill dynamism in geometry. Because up to that point, of course, many people have been making arguments that were time-based. But one of the intellectual figures who stands behind the Elements, over here, this scary fellow, is Zeno. And Zeno introduces various paradoxes of time that complicate mathematicians' ability to take time-based arguments as foundation. So in fact, one of his famous paradoxes of time also involves an arrow. And Zeno imagines us shooting this arrow at someone. Euclid just happens to be in the way. And he asks, well, how does the arrow move? And the arrow travels through time from the bow to Euclid. But what is time? And he finds the answer. Time is a succession of instants. And there's his paradox, because if we look at an instant, there's one, we see the arrow's not moving. And if you look at another instant, the arrow's not moving over there either. So if time is only a succession of instants, there is no place in time where the arrow actually moves, and so the arrow never leaves the bow. Good thing for Euclid. But this is sort of the rationale behind Euclid's desire to move away from time and time-based forms of reasoning that are very evident in pre-Euclidean geometry. So let me restore the Elements to their hallowed place here. I'm getting ahead of myself, but I wanted to point out how the pieces of my talk sort of interact, focusing on Euclid, but taking the dynamic geometry perspective. And now that I've shown my sort of fanciest sketchpad slide, I can actually turn to the structure of the talk. So I'm going to reintroduce or introduce you to the Elements, just very briefly. And then basically what I'd like to do is recontextualize, repersonalize, and retemporalize the whole context around the whole setting of the Elements. So we'll look at where do the Elements come from, who is Euclid, and where are his ideas being influenced from. And then what are they really like? Open up the book and go in depth into book one of the Elements. And then finally, what happened next? How did things evolve from Euclid? So just very briefly, should you not remember your Elements, the Elements are composed of 13 different mathematical treatises. and they cover a wide variety of subjects of mathematics in antiquity. You can group them loosely into sort of three major clusters. There are books that are about plane geometry, there are books about ratio and proportion, and there are books about solid geometry. And historians quibble as to what the purpose of these books was. So one argument is that they're simply a compendium of Greek mathematics brought together under a new and sort of more rigorous way of arguing, and that they're clearly influenced by lots of mathematics of the time. But the other idea is that they're actually all a single argument leading up to Book 13, the final demonstration that there are 5 and only 5 Platonic solids. And neither of these explanations really fits well. If it's the former, it's much too sort of teleologically directed. It has momentum. Things build and build in a way that in an encyclopedia is usually just ordered by the alphabet or time or something like that. On the other hand, if it's an argument about the Platonic solids, there's much too much in it. There's lots of stuff that gets developed and then not used again. So I think both of these tensions are there. Clearly, Euclid has an argument running through the elements, but he's including lots of stuff that he thinks of as foundational. So with that overview of the elements, I wanted to turn to Euclid himself for a minute. What's great about Euclid is we know absolutely nothing about him. So he's a figment of our imagination. And that imagination starts sort of, the first biography we have of Euclid is a paragraph long and comes from 800 years after he died. So think about that. It's drawing on texts that are now lost and so forth. But we can quote it in its entirety, and that's what I've done here. It's a bit to read, so I'll read it out. This is Proclus, writing in the 5th century. So not long after these other people I was talking about came Euclid, who brought together the elements, systematizing many of the theorems of Eudoxius, perfecting many of those of Theaetetus, and putting in irrefutable, demonstrable form propositions that had been only rather loosely established by his predecessors. He lived in the time of Ptolemy I, for Archimedes, who lived after Ptolemy, mentions Euclid. It's also reported that Ptolemy once asked Euclid if there was not a shorter road to geometry than through the elements, and Euclid replied that there was no royal road to geometry. So even the king has to do his homework. He was therefore later than Plato's group, but earlier than Eratosthenes and Archimedes, for these two were contemporaries, as Eratosthenes somewhere says. Euclid belonged to the persuasion of Plato and was at home in his philosophy, and this is why he thought the goal of the elements as a whole to be the construction of the so-called Platonic figures. So Proclus is taking a stance on the purpose of the elements, but he's also giving us essentially a word problem. The question is, when was Euclid? And the answer is this sort of complicated formulation of reference points to all of the other mathematicians that we know about from the era. So who were these people? Well, this story really begins with the other mathematicians Proclus has been talking about. Pythagoras, of course, we know from his theorem and the rather sort of mystical work on whole number and ratio and the relation to music. Basically, most of what we know about Pythagoras is compatible with what today we would call a cult leader of a bunch of sort of mathematical wackos. Thales, a much more sort of foundational figure in both philosophy and mathematics. He's really the first person to reject mythological explanations in looking for understanding of phenomena, and instead to stress reasoning and deduction. So the Euclidean deductive tradition begins here, and some people consider Thales the first Western mathematician. Then we get two more mathematicians, Eudoxius and Theaetetus, contemporaries. Eudoxius basically contributes Book 5 to the elements. So the Pythagoreans have a crisis about rationality that causes the very idea of proportion to be as worrisome in this era as time is to Euclid. And Eudoxius returns us to the ability to use proportion. Book 5 comes from him. Theaetetus, interestingly, is the one who proves the Platonic solid result that is the crowning achievement of the elements. So this is not Euclid's work, it's Theaetetus's. And let's actually pop over and look at that. So Platonic solids are polyhedra with convex polyhedra with regular polygonal faces. And the question is, how many of these are there? So Theaetetus approaches that beginning with two sort of first principles that we can reconstruct just thinking about a vertex of a Platonic solid. And view the vertex. Okay, so the question is, how many polyhedra, or how many polygons can meet at a vertex? And what can we say about their angle? So obviously, if there's only one polygon, you don't have a meeting, you have a solitary game. If there are two polygons, then either there's space around them, or they meet in an edge rather than a vertex. So the smallest number of polygons you can fit around a vertex in a polyhedron is 3. You can fit 4, 5, or 6, and more, but we know 3 is the minimum. Then in terms of the angles, if we were on the plane, we would expect a vertex to be surrounded by 360 degrees. But this is convex, so it can't be as big as 360 degrees because the whole thing would flatten out. So you put these two pieces together, and you come up with a simple rule for the possibility of a Platonic solid, which is the number of your faces times their internal angle has to be less than 360 degrees. And once Theaetetus has this notion, it's simply a counting game. So here I have a variety of faces. A regular triangle has a 60-degree edge, interior angle, regular square, 90 degrees. And I'm multiplying this by some number of faces. Now we said 1 doesn't make sense as a number of faces. Let's go to 3. And the question is, when is this product less than 360 degrees? That's a place where you'll find a Platonic solid. So here's one right here, 3 triangles meeting at a vertex. That's our tetrahedron. Here's another product under 180. 3 squares, that's a hexahedron. 3 pentagons, a dodecahedron. But when we get to hexagons, we can't put 3 of them around a vertex because it would be flat. That's the tiling of the plane, not a convexity. So let's try 4. When you go to 4, you get another possible configuration with triangles. That's your octahedron, 4 at a vertex. But by the time you look at fourgons, you're already at 360 degrees and only getting bigger. So there are no other Platonics that meet 4 faces at a vertex. At 5, there's one last one, 5 triangles at a single vertex, the icosahedron. And after that, all of your values are 360 degrees and increasing upwards with either m or theta. So that's the exhaustive catalog of Platonics, and Theaetetus works that all out. Interestingly, there's no evidence before him that people knew of more than 3. So perhaps Theaetetus also discovers the last 2 Platonic solids. All right, where are we? Back to Ptolemy. He's the king. General of Alexander the Great, moves to Egypt, sets up a dynasty of kings that lasts for 300 years. All of them very conveniently are also named Ptolemy, except the last one, who's Cleopatra. Then you have now sort of my 2 favorite players in the ancient Greek mathematics, Eratosthenes and Archimedes. So with these people, it's a question of where do you begin and when do you want to stop. Eratosthenes, he's the first geographer. He first coordinatized a map of the world, invents the latitude and longitude, figures out how big the circumference of the Earth is, calculates the Earth to the sun. I think in our units, he says it's about 149 million kilometers. NASA says on average it's 149.6. calculates the distance of the sun to the moon, invents the armillary sphere, which is a sort of manipulative for looking at astronomical trajectories, music theorist, his algorithm for coming up with prime numbers. All of this in his spare time, because he's also the chief librarian of the Library of Alexandria. So I tend to think of myself as accomplished when I get to the grocery store and the dry cleaner on the same day. This is just another lead of productivity. Let's look at Eratosthenes' calculation of the circumference of the Earth, just very quickly from the dynamic perspective. You've got the Earth, and thanks to good records, the technology of writing with him as librarian, he knows that there's a place not far from where he lives, Swenet, where when the Earth is shining, when the sun is shining down on the Earth, there are no shadows. And in fact, the early writings on Eratosthenes talk about a well deep in the deep well in Swenet, that when you look in on the solstice, your reflection blocks out the sun. The sun is exactly overhead. And it turns out that Swenet, it's where the big dam is on the Nile, and it's just on the Tropic of Cancer. So at the solstice, the sun really is just overhead. Here's the sun shining down. And Eratosthenes assumes that all of the sun's rays are falling parallel. So let's construct a parallel on top of this flagpole in Swenet. And notice that as the sun's orientation changes over the year, casts a shadow, but there at the solstice, there is no shadow. Now, this is the Nile. It's been extensively surveyed for thousands of years. Eratosthenes has a very good estimate of how far it is from Swenet down the Nile towards Cairo and Alexandria, where he is. So essentially, he knows the distance of this little arc right here, which I'll construct and then measure. So for that sized Earth, it's only 3 centimeters between Alexandria and Swenet. Now, if you look at our line passing directly through the vertical at Swenet, our sunbeam, and consider a parallel sunbeam hitting a flagpole at Alexandria, you see his simple result as a traversal crossing 2 parallel lines. He can measure this angle easily, the angle of a shadow in Alexandria. And he knows that that is equal to the angle formed at the center of the Earth between Alexandria and Swenet. And whatever that angle is some fraction of the 360 degrees around the entire Earth. So 360 degrees divided by that angle that he's measured in Alexandria says that the Earth is going to be 16 times the circumference, or 16 times the distance between Swenet and Alexandria. That gives us an estimate of 47 centimeters, the true Earth. 47 centimeters as well. Better than an estimate. I usually don't find it quite so accurate because, of course, this depends on our parallels. Okay, so Eratosthenes is also friends with Archimedes. And Archimedes is, a famous engineer, a famous scientist, measures methods of exhaustion, the quadrature of the parabola, the lever, on and on and on. Where Archimedes figures for me in an interesting way is that Archimedes is really a tremendously dynamic geometer. So we think about his methods of exhaustion, and they're iterative. Let's look at Archimedes' estimate of pi for a minute. So he needs to accurately measure the circumference of the circle, and of course you can't do that with a floppy measuring stick. So in order to come up with pi, he wants to know the circumference so that he can divide by the diameter. But what he does know easily how to measure the area are polygons. So we'll start with n equals 3 and simply estimate the area or the circumference of the circle as the perimeter of this polygon. And because at this point he already knows how to inscribe and circumscribe polygons, he knows the area is bigger than this and smaller than a circumscribing polygon. We can construct one here. I'm going to construct tangents to the circles passing through my inscribed triangles vertices and make those vertices the midpoints of a regular polygon that circumscribes the circle. Okay, so we did 2 perimeter estimates. The true circumference of the circle is bound between those, and at that point we can just start looking at bigger and bigger polygons. Now Archimedes actually develops a numerical technique for doubling the number, for computing the perimeter of a polygon with twice as many sides as this given polygon. So rather than work out this sequence, 3, 4, 5, 6, 7, he goes from 3 to 6 to 12, and eventually up to 96 gons before stopping this arbitrarily extensible process and coming up with his estimate of pi. So the method of exhaustion is one example of a dynamic process. In time, as you continue this sequence, you are exhausting the area of the big polygon by gobbling it up with the small polygon. But much more than that, Archimedes used tools different than the compass and straightedge for doing his geometry. He was a proponent of what's called in Greek the noesis construction. That was very popular in its day, in fact more popular than Euclid's tools. But in a noesis construction, the critical move is being able to slide your straight edge around on the plane with mathematical control. We think of that now as a marked ruler. An earlier term for it in English is a verging construction, but I don't really understand the sense of that term, so I just call them noesis constructions. But once you can slide things about on the plane, obviously you can start doing things that you can't do with a compass and straightedge. So one noesis construction, I think I won't show it for time, is the trivial trisection of the angle. You can't do that with compass and straightedge. All right, so all of these people fit together into this complicated timeline, and Proclus gives us Euclid somewhere in the center of it. Oh, I've left off Plato. Plato's over here. He's not a mathematician, but he's a mathematical enthusiast and a research director and a cheerleader for mathematicians, so many of them spend time with him. So we don't know how long Euclid lived. We don't know where he was from. He winds up in Alexandria around 300. I want to go back to Archimedes for just a minute because there's lots of interesting Archimedean developments just within our century. So Archimedes dies. He's killed by a Roman soldier who kills him for disrespect because Archimedes says that he wants to finish working on the math problem he's working on before he goes to dinner with the general that the soldier has come to take him to. And he gets buried, and his famous tombstone with the sphere and the cylinder about his result is constructed. The last person in antiquity to know where that tombstone was is Cicero, and then it's gone. It turned up in 1960 in a hotel foyer outside in suburban Syracuse, and then within 10 years was lost again. They just lost track of where it was. It's not that it was stolen. They misplaced the records. So maybe it will turn up again. Beautifully, this is something that turned up again. About 12 years ago, this sold at auction for $2 million. It's a 13th century prayer book with which, using high-end digital techniques, you can read beyond the prayers to see what had been erased, what had been on this papyrus earlier than the prayers. And it turns out 7 treatises of Archimedes were on this papyrus, 2 of them previously unknown. So there's been a lot of new work from Archimedes just within our lifetimes. And if you want a true life Da Vinci Code, I recommend reading the Archimedes Codex. I'll put up this link at the end. Great book, reconstructing sort of the paleo geometry of Archimedes. All right, here's the timeline. There they all are. There we are. Pretty thin slice of Greek history there. And looking at them in time, that's also just, they love measuring the earth. Let's put them on the map too. So it sort of starts here in Asia Minor. Thales is from here, Pythagoras here. Plato's group is here, Eudoxius and those people. Archimedes comes from Sicily. Eratosthenes comes from here. Many of them wind up here as the center of learning in antiquity. Nobody goes down here, but they know how far it is, so they can measure the circumference of the earth. All right, that's the background. And now we can really turn and take a closer look into the elements themselves. And I'm going to just focus here on book one, which is the masterpiece. It's the masterpiece in the sense that its deductive framework is well developed. It's complete. All of the other ones, basically the other books, lack postulates. They're much looser in terms of their derivations. But book one has 4 parts. The first of which is a set of definitions that work very differently than our definitions. For us, a mathematical definition says something mathematical. For Euclid, the definitions are actually a bit of context. They're very common sense ideas that are meant to communicate what he's talking about without rigor to them. The postulates are the real heart of the axiomatic framework. Euclid gives us 5, and the first several are phrased as constructions. So he postulates, he assumes you know how to draw, or that you can draw a single straight line from any point to a point. We would say this differently. We would say 2 points determine a line or something. But he's very tool-based, production in time, very time-based. And so you have the ability to extend from a segment to a bigger segment, or to a ray, or to a line. You have the ability to use a compass and make a circle, given a center and radius. A basic fact about angle equality. And then this monstrous 5th postulate, which is, in Euclid's phrasing, difficult even to parse, much less to understand. I'll substitute it here for Playfair's version, a little closer to our sense of it. But it's the parallel postulate. And it says that through a point not on a line, there is a unique parallel line. One line passes through that point that does not intersect the first line. And the problem with this postulate historically is that it's not self-evident. All of the others can be, in some sense, reconciled with intuition or facts of the universe or something. But this is a complicated statement. And so, beginning already in Euclid and continuing for thousands of years past them, mathematicians have questioned this, tried to see whether it fell out from the other postulates, and wondered whether it was strictly necessary for Euclidean geometry. So those are the postulates. They're followed by what turn out to be a bunch more postulates, though we don't call them that. We call them common notions. And these are basically not axioms about geometry. They're axioms about magnitudes more generally. But he does use them in exactly the way of postulates. So we put these 5 together for the axioms of Euclidean geometry. And then the propositions. And this is what he develops with all of these given ideas represented by the previous sections. And the propositions tell a very coherent story in which you do as much geometry as you can while avoiding the 5th postulate. And then eventually you introduce the 5th postulate. So many people interpret this as evidence, the fact that there's no use of parallels until the 27th proposition is evidence that Euclid himself was uncomfortable about this. Once you have parallels, you can build parallelograms. And once you have parallelograms, you can begin making arguments about area conservation. And that leads you up to all you need for the Pythagorean theorem. So I want to visit just a few of these propositions so that we can see what they look I will very rapidly abandon Euclid's wordings, though, because he's very sort of prolix. He repeats everything, once without labels, then once in reference to a diagram. So the first proposition, on a given finite straight line, to construct an equilateral triangle. And this is essentially a recipe. So with center A and distance AB, let the circle be described. And when he says be described, he's invoking that third postulate that we know how to describe a circle with a center and radius. And then with center B coming back to A, describe another circle. And then join A and B to where the two circles meet, and you have your equilateral triangle. The proof follows. It's straightforward. These are all radii of equal circles, and so they're all equilateral. So this proposition is essentially a construction recipe. The first several are, although the first several constructions get much more delicate than the equilateral triangle. But by the time we get to proposition 4, we have a real theorem. And I won't read all of this, but let's just start it out. If two triangles have the two sides equal to two sides, respectively, and have the angles contained by the equal straight lines equal, they will also have base equal to base. And that should be enough to summon the simplified version. We have two triangles that share a side, an angle, and a side. And with our more modern idea of congruence, we can vastly shorten the statement of the theorem, because we don't have to say everything is pairwise equal. We can just say the whole things are equal. What about the proof, though? Again, we don't have to read it far to find the punchline. So his proof begins, for if the triangle ABC can be superimposed on the triangle DEF, so let's bring this over here, and if the point A can be placed on the point D, and the line AB over on the line DE, then everything lines up. But wait, this is Euclid doing dynamic geometry. How do you superimpose ABC on DEF? Well, you drag it. And the problem is this is completely unjustified in the axioms because he doesn't want you dragging anything. So the very first real theorem turns out to require dynamism, even though he's driving us away from it. And this causes, people like Bertrand Russell. Russell says that this whole proposition is a tissue of nonsense because of this weakness to its argument. Someone famously responded that Russell's problem with Euclid appears to be that Euclid has not read Bertrand Russell. My view is we could be a bit more charitable to Euclid here, because this is the standard way of reasoning here. There are all sorts of unfounded claims in Euclid that invoke the fact that we take many things, many ways of knowing for granted and many ways of reasoning for granted. I think this is less of a big deal than for instance, Russell is. I think if Euclid wants to let his triangle slide around, well, we should let it slide. So there, again, this seems to me to be a minor quibble with Euclid, but I do point it out because I think that the idea that dynamism's absence in Euclid geometry gets underwritten is interesting from a perspective of someone whose main work is in dynamic geometry. All right, on to the section. The third part of Book 1 is about parallels. And Euclid spent a lot of time sort of getting to set up this situation in which parallels cut by a traversal give us various corresponding angles that are congruent. And again, if he had dynamism, this would be much simpler. I think a beautiful way of thinking about this is that you don't have different angles that correspond, that you simply have the same angles here being sort of translated out. But once you have these correspondences, you can come to the grand result at the end of the whole section on parallelism, which is the interior angle sum of a triangle. So with a triangle and this derived knowledge of parallel lines and their angles. We'll construct parallel to the base passing through the opposite vertex, and then reason that this angle B down here is the same as this angle up here. This angle C is therefore the same as this angle, again because of the parallel. And this angle here is equal to itself. So the final two propositions in this section show us that in a triangle, the interior angles add up to a line, and that if you have three interior angles that add up to a line, you have a triangle. So it works both ways. And all of that depends on the fifth postulate, in the sense that you need this unique parallel here. Changing the triangle is simply changing the direction in which the traversal cuts it, not changing the equality of those corresponding angles. Good. So as I said, parallelism gives him the ability to argue about transformations of area, squares becoming parallelograms with equal base and height, or triangles of equal base and height preserving their area. And that sets up everything he needs for the Pythagorean theorem. And this is a real sort of triumph of deductive reasoning, in the sense that the argument is in no way intuitive or obvious, but that once you work through the steps, each follows cleanly from the last, and the result is beautiful. And basically, I'll just sketch his argument, because without dynamism, it's somewhat involved. But he cuts the Pythagorean theorem in half into separate squares on the sides and separate parts of the square on the hypotenuse. And then he's going to solve the problem just for half and assume that the same solution works here. Then he does exactly the same thing. He cuts these in half and says, if I can show that half of this is equal to half of this, I've shown that all of this is equal to all of this. So half of this and half of this are two triangles, and they wind up being equal in area by his parallel line arguments to two triangles that you can find in this configuration. And those two triangles are basically that one and that one. And if you think of these, let's look at them. Both of them share one side, which is equal to a side of the square on the hypotenuse, one side which is equal to the edge of the square we're trying to prove is equal to this half of the square on the hypotenuse. And they share a common angle, which is this angle B plus 90 degrees, either 90 degrees this way for my first triangle or 90 degrees that way. So you get equal triangles, you change those equal triangles into equal half rectangles, you double that into equal whole rectangles, and you've just proven that half of a Pythagorean theorem equals half of a Pythagorean theorem. Double that again, and you come back to the whole. Following the whole argument from a dynamic perspective, still very much the spirit of Euclid's argument about preserving area, what we're doing here is shearing these two squares. Their width and height are invariant across that shear, and so the area of the parallelogram that gets formed is the same as the area you started with. You shear again, and now you've added a squared plus b squared into a new square, which is c squared. So this really is Euclid's proof, if you put time back into it. All right, that's the beautiful result of the foundations of plane geometry according to Euclid. When Pythagoras worked this out, he offered a hecatomb to the gods. A hecatomb is 100 sacrificed cows. So this theorem was worth 100,000 pounds of beef to the Pythagoreans. Creepy. But it's also, the foundation of mathematics. So this is the structure of the elements. Book 1 at least. And book 1 is essentially the most significant book in terms of its axiomatic integrity. And it's the book that we come back to in the long history of use received Euclid. And I'd like to turn for the last part of that to sort of what's happened since Euclid and since the elements came around. And there's been lots of constancy in this story, but also lots of variation. One form of variation that's very interesting to me is sort of the pedagogic variation. How can we teach this better? If this is the best textbook that's ever been, how can we improve it? A beautiful high point in that 2 millennium old narrative of how do you teach Euclid comes with Burns' edition of Euclid from the 19th century. Burns decides that students need to do more visualization and that they get lost in all of this translation back and forth between the figure and the explanation. And so he comes up with a Euclid in which he's replaced all of the labels with pictures of how it looks in the diagram. So there's a literal correspondence now rather than a symbolic translation between the description and the diagram. It's sort of my life's ambition to someday build a version of Burns that is dynamic. So this is a proposition 1 of the elements, the way Burns does it, reinterpreted in Sketchpad. So he says, given a finite straight line, namely this thing, this little black thing, to describe an equilateral triangle, you want to make a circle like that with respect to your black line, and a circle like that, and onward and onward and onward. Now, Burns' Euclid is absolutely beautiful and is super famous, but not at all in math education, because it never made it into the schools. It was much too expensive, and in fact, it drove its publisher, who was one of the biggest publishers in England at the time, completely out of business, because it was the most expensive book ever to have been produced at the point that it was produced. So it's really famous in the graphics design community rather than in the math education community. Also, of course, after Euclid, there's been the 2 millennia of impact of Euclid on the development of mathematics. So for hundreds of years after Euclid, people basically work in the Euclidean tradition, extending the results, applying the same postulates, Apollonius with his tangencies and conics. But then Greek wisdom goes off and is safe harbored in Islamic thought during Europe's long dark ages, and there they start commingling it with their ideas about algebra, and basically begin developing the stuff that Descartes takes further with analytic geometry. Newton wrenches us back to Euclid by coming up with a view of space that basically is a Euclidean view, and with Euclidean arguments about the homogeneity of space, which was by no means a given at the time gravity comes in. And then the greatest story of them all is, of course, the hyperbolic geometry story, in which after 2,000 years of trying to prove that the 5th postulate is necessary, a whole bunch of people at the same time, Gauss and Bolyai and Lobachevsky, all find that alternate versions of the 5th postulate, in which there are no parallel lines, or in which there are many parallel lines, are just as consistent in the geometries they come up with. So this is the Poincaré's model of a geometry that is every way like Euclid's, except rather than one parallel line, you have more than one parallel line through a point, not crossing a given line. What does it mean to be a model? Well, Poincaré is doing 2 things by coming up with a technique for essentially interpreting in the Euclidean plane this idea of a non-Euclidean geometry. One, Poincaré is a huge believer in visualization and in mathematical intuition, and he wants a playground. It's about being able to see this and to work in a non-symbolic and propositional fashion. Second, though, if you can correspond each piece of your hyperbolic theory to the Euclidean theory, then you gain the legitimacy of the Euclidean theory for your hyperbolic theory. Which is to say, if Poincaré's model is complete, then hyperbolic geometry is just as consistent as Euclidean geometry. You can't prove Euclidean geometry is consistent. 2,400 years might pass and we might discover it's not. But by building a model of hyperbolic geometry in Euclidean geometry, we can prove that one is as consistent as the other. So it's a legitimacy here. So in the Poincare model of hyperbolic geometry, a line, the infinite plane sits inside a Euclidean circle. So we call it the disk. The interior of this disk is the infinite plane. And that means, just like in the Euclidean plane, between any points there's a finite measure, but we can keep going an infinite distance before we hit the end of this line. So you never get to the border of the disk because there's infinite distance between C and the disk at all times. So that leads to some interesting consequences. In our view of this, things are going to look curved, and there's lots of logarithmic behavior as you approach the edge of the circle that models the plane. Let's look at the fifth postulate here by taking a given line, AB, and a point not on it, D, and seeing if we can construct a parallel line that does not intersect our given line passing through D. So there's one. They don't cross within the hyperbolic plane. But this line, DF, also doesn't cross AB. So that's a second parallel. And you can see I can add as many as I want here. There are more than one parallel line, all of these parallel to this given line. That then changes the set of things that we can bring forward from Euclid, because that's different from Euclid. So what can we bring forward? One thing easy to bring forward would be the first proposition I showed you, the equilateral triangle. That only depended on having a compass and a straight edge. So I'll draw a hyperbolic segment. I'm repeating proposition 1, which basically depends on postulates 1 and 3 of Euclid, but not on 5. And I draw two circles and go back to the straight edge to complete the equilateral triangle. And this odd-looking thing is a hyperbolic equilateral triangle. It didn't depend on parallelism. Doesn't look equilateral to us, or equiangular. But of course, if we measure it inside its hyperbolic context, or I'm measuring its angles, we should see, so there's L, K, and J, that all three of the angles are the same. Now they're the same, but they're certainly not 60 degrees. Right? So let me add them up. We'll look at the sum of the interior angles of an equilateral and equiangular hyperbolic triangle. And here they're only 152 degrees. Now, if that seems odd, go back to proposition 32, where we learned that the way we know we have 180 degrees in our triangle is by being able to construct a unique parallel line. We no longer have that unique parallel line. So they can't be 180 degrees, because if they were, we would have a Euclidean triangle. All right, so as we explore this dynamically, what you see is that in the hyperbolic plane, size and angle are dependent. The smaller the triangle is, the bigger its angles. Getting bigger, bigger, bigger. What's the limit look like? We're approaching 180, but we can't get there, because if we got there, we would be in Euclidean plane. Similarly, as we come out to huge triangles, those angles get tighter and tighter and vanish towards 0, the sum of the angles. So you have an infinite number of angle sums for an equilateral triangle. That gives rise to one of my favorite, certainly one of the most beautiful results, which is to come back to our very first piece of mathematics, Theaetetus, and think about that construction of the Platonic solids. in the plane, you can apply the same sort of logic to figure out tessellations of the plane by regular polygons, rather than closures of a convexity by regular polygons. And what you're looking for is how many regular polygons fit around a vertex so you get 360 degrees. If you have equilateral triangles, the answer is 6. They've got a 60-degree angle, and 60 times 6 equals 360. To tile the hyperbolic plane, then, how many equilateral triangles can you fit around a point? There's still 360 degrees around it. You know you can't fit 6, because if you fit 6 exactly around it, they would need to have 60-degree angles, and that would mean that they'd be Euclidean triangles, and you'd be in the Euclidean plane. But you could have 7. 360 divided by 7. If you could find an equilateral triangle with 51.5-degree interior angles, you could fit 7 of them around a vertex. And of course you can find them, because you've got a whole continuum of them between 0 and 180. So let's just quickly repeat the construction of the equilateral triangle a lot of times. And here I'm going to iterate this construction on its edges. It's best when I iterate if I don't have all my measures shown, because I'll get lots of iterated measurements too. J to K. So J to K describes my construction with the equilateral triangle on the left. So I want to apply that to K to J, which should give me an equilateral triangle to the right. And I want to apply it to, at the same time, to L and K, which should give me now a branch going to the left, lower left, and then I want to apply it to J and L, which should give me a branch coming off here. So I'm developing a fractal out of these equilateral triangles. And now all I have to do is vary the size of my equilateral triangles to find these angles. So right here I have 1, 2, 3, 4, 5, 6, 7 equilateral triangles meeting at a vertex, tessellating the hyperbolic plane. If I make the triangles somewhat bigger, their angles get smaller, and that means I come to a point where I can find 8 or 9, and on and on and on as the triangle gets bigger and bigger and bigger. So where in the Euclidean plane there are a fixed number of regular polygon tessellations, in hyperbolic plane there's an unlimited number. So looking at what's happened since, basically, on the one hand, there's a lot of stasis. 2,300 years of teaching Euclid, and 2,300 years of that being the curriculum. And today there's no curriculum decision in geometry that is not pretty directly influenced by the elements. And certainly most geometry textbooks, high school and college, still directly pattern themselves, at least in parts, on the derivations of Euclid and the elements. I think this is both, from a student's perspective, the greatest horror and the greatest strength of mathematics simultaneously, though not necessarily simultaneously to each student. On the other hand, against all of this stasis, there's also a lot of change. There's an evolution in mathematics and in pedagogy, non-Euclidean geometries, things like Bern. But I also think of this history in terms of history of technology. Before Euclid, people aren't writing things down. Writing is a new technology in Euclid's era. Plato, for instance, is very suspicious about writing and thinks if you start writing things down, your brain will rot because you'll forget how to memorize. Euclid is as much a function of writing as the elements is a function of Euclid, in that once you can write, you can develop this sort of prodigious and monumental logical derivation chains that dwarf the ability to memorize and recapitulate. That writing basically doesn't give birth to geometry. It basically kills it stone cold dead, because papyrus is very difficult to share. You have to travel to Alexandria to read it. It becomes something that very few people can do or pursue, and it's a life's quest to read 2 or 3 different versions of Euclid for 1,000 years, so that you can figure out how each one's errors get canceled out by the other 2. The printing press, new technology, suddenly Euclid's in print, and we can all buy a copy for $1.99, and you get, you know, an explosion in modern mathematics. And these ideas are now all over the world, and people are talking across great distances. Technology, the digital technology comes along, and you have logo first, but then the mouse as a piece of technology comes along, and you get dynamic geometry second. So this is a whole progression of development and evolution, not just in our tools, but also in our thinking, because our tools always mediate our thinking. So I guess this leads us with the conclusion that the more things stay the same, the more they change. And on that note, I'll end. Thank you.